There are secrets in the universe so profound, so unsettling, that even the greatest minds in science have struggled to comprehend them. Among those minds, Richard Feynman stands out, not just for his genius, but for his relentless curiosity and his willingness to ask the questions others were too afraid to voice. Feynman's journey through the mysteries of space led him to a discovery that would shake the foundations of physics and challenge our most basic assumptions about reality. This is the story of how Richard Feynman exposed a dark secret of space, a secret that continues to haunt scientists to this day. To understand the magnitude of Feynman's revelation, we need to step back and consider what we thought we knew about space. For centuries, space was seen as a vast, empty void, a stage on which the drama of the universe played out, but not an actor in the story itself. Newton imagined space as an infinite, unchanging backdrop, a container for matter and energy, but not a participant in their dance. Even Einstein, who showed that space could bend and warp under the influence of gravity, still saw it as a kind of fabric, flexible, yes, but ultimately passive. But Feynman, with his unique blend of skepticism and imagination, saw something deeper. He realized that space is not empty. In fact, it is seething with activity, alive with fluctuations and possibilities. This insight came from his work on quantum electrodynamics, the theory that describes how light and matter interact at the smallest scales. In the quantum world, nothing is ever truly at rest. Even in the coldest, darkest reaches of space, particles and antiparticles are constantly popping in and out of existence, borrowing energy from the vacuum and then vanishing before they can be observed. This phenomenon is known as vacuum fluctuations, and it is one of the strangest predictions of quantum physics. Feynman's calculations showed that these fluctuations are not just a theoretical curiosity, they have real, measurable effects. For example, the so-called Lamb shift in the energy levels of hydrogen atoms can only be explained by taking into account the restless activity of the vacuum. The Casimir effect, another bizarre consequence, occurs when two metal plates are placed very close together in a vacuum. The plates are pushed together by the pressure of virtual particles, a force that arises from the quantum froth of empty space. These effects have been confirmed in experiments, leaving no doubt that the vacuum is far from empty. But the implications go even deeper. If space is filled with energy, then it should have a measurable effect on the universe as a whole. In fact, when physicists try to calculate the total energy of the vacuum using quantum field theory, they arrive at a number so large that it defies comprehension. The so-called vacuum energy should be enough to blow the universe apart, to overwhelm the force of gravity and send galaxies flying away from each other at unimaginable speeds. And yet, when we look at the cosmos, we see something very different. The universe is expanding, yes, but at a rate that is far slower than the vacuum energy would suggest. This is the dark secret that Feynman helped to expose. Our best theories predict that empty space should be filled with an enormous amount of energy, but the universe we observe does not behave as if that energy is there. This discrepancy is known as the cosmological constant problem, and it is one of the greatest unsolved mysteries in physics. The numbers are not just a little bit off. They are off by a factor of 10 to the 120, the largest mismatch between theory and observation in the history of science. Feynman was both fascinated and disturbed by this result. He saw that it pointed to a fundamental gap in our understanding of the universe, a place where the laws of quantum mechanics and the laws of gravity collide and fail to make sense. He called it the worst prediction in physics, and he was not alone. Generations of physicists have struggled to explain why the vacuum energy does not seem to have the catastrophic effects that theory predicts. Some have suggested that there is a hidden mechanism that cancels out the vacuum energy, a kind of cosmic balancing act that keeps the universe stable. Others have proposed that our theories are incomplete, that there are new laws of physics waiting to be discovered. Still others have speculated that the answer lies in the multiverse, that we live in one of many universes, each with its own value of the vacuum energy, and that we just happen to be in one where life is possible. But for Feynman, the mystery was a source of wonder as much as frustration. He saw it as a reminder that the universe is stranger than we can imagine, that our theories are always provisional, and that the search for truth is never ending. He urged his students to embrace uncertainty, to question assumptions, and to keep pushing the boundaries of knowledge. The dark secret of space that Feynman exposed is not just a technical problem for physicists to solve. It is a window into the deepest workings of reality, a challenge to our most cherished beliefs, and an invitation to explore the unknown. It reminds us that, for all our progress, we are still standing on the shore of a vast, uncharted ocean with mysteries waiting just beyond the horizon. To truly appreciate the magnitude of the dark secret Feynman uncovered, we need to look at how this revelation has rippled through the world of physics. The idea that empty space is not empty, but instead a bubbling sea of quantum activity is so counterintuitive that it challenges our very sense of reality. For centuries, philosophers and scientists alike imagined the vacuum as a void, a nothingness. But Feynman's work and the experiments that followed forced us to confront a new truth. The vacuum is alive. This realization has profound consequences. If the vacuum is filled with energy, then it must exert a force on the universe. This is not just a theoretical curiosity. It's a fact with observable consequences. In 1998, astronomers made a discovery that would shake the foundations of cosmology. The expansion of the universe is accelerating. Distant galaxies are not just moving away from us. They are speeding up, as if some mysterious force is pushing them apart. This force has been dubbed dark energy, and it now appears to make up about 70% of the total energy content of the universe. At first glance, it might seem that dark energy is the missing piece of the puzzle. The vacuum energy predicted by quantum theory finally revealed in the motion of the cosmos. But there's a catch. The amount of dark energy inferred from astronomical observations is tiny compared to the vacuum energy predicted by quantum field theory. The numbers are off by a staggering 120 orders of magnitude. It's as if you calculated the weight of a feather and got the mass of the sun. This is the cosmological constant problem in all its glory. Our best theories predict a universe that should be violently unstable. But what we see is a universe that is, for the most part, calm and orderly. Feynman was deeply troubled by this mismatch. He knew that it pointed to a fundamental flaw in our understanding of the universe. If the vacuum is so energetic, why doesn't it tear the universe apart? Why is the cosmological constant, the term Einstein introduced to describe the energy of empty space, so small yet not exactly zero? These questions remain unanswered, and they haunt physicists to this day. The search for answers has led to some of the most creative and daring ideas in modern science. Some theorists have proposed that there is a hidden symmetry in the laws of physics that cancels out the vacuum energy, leaving only a tiny residue. Others have suggested that the value of the cosmological constant is set by chance, a kind of cosmic lottery that determines the properties of each universe in a vast multiverse. In this view, we live in a universe where the vacuum energy is just right for life to exist, not because of any deep principle, but because we couldn't be here to ask the question otherwise. Feynman, ever the pragmatist, was skeptical of explanations that relied on chance or anthropic reasoning. He believed that the answer must lie in a deeper understanding of the laws of nature, a new theory that would unite quantum mechanics and gravity and reveal the true nature of space and time. This quest has driven generations of physicists to search for a theory of everything, a single framework that can explain all the forces of nature, from the smallest particles to the largest structures in the cosmos. But the path has not been easy. The mathematics of quantum gravity is notoriously difficult, and progress has been slow. String theory, one of the leading candidates, offers the tantalizing possibility that the vacuum energy is determined by the shape of extra dimensions curled up at every point in space. But so far, no one has been able to calculate the value of the cosmological constant from first principles. The dark secret of space remains just out of reach, a riddle wrapped in an enigma. Yet for all the frustration, there is also a sense of wonder. The fact that we can even ask these questions is a testament to the power of human curiosity and imagination. Feynman understood this better than anyone. He saw science not as a collection of facts, but as a way of seeing the world, a process of exploration, discovery, and awe. He urged his students to embrace the mysteries, to delight in the unknown, and to keep pushing the boundaries of knowledge. The story of the vacuum is a perfect example of this spirit. What began as a simple question, what is empty space, has led to some of the deepest and most profound mysteries in all of science. It has forced us to rethink our assumptions, to question our theories, and to confront the limits of our understanding. It has shown us that the universe is not a static, predictable machine, but a living, dynamic system full of surprises and secrets. And the journey is far from over. New experiments are probing the vacuum with unprecedented precision, searching for signs of new physics. Astronomers are mapping the expansion of the universe, looking for clues to the nature of dark energy. Theoretical physicists are exploring bold new ideas, from holographic universes to emergent space-time, in the hope of finding a solution to the cosmological constant problem. Feynman's dark secret of space is a reminder that the universe is always more mysterious than we expect. It challenges us to keep asking questions, to remain humble in the face of the unknown, and to find joy in the search for truth. For in the end, it is the questions we ask and the mysteries we embrace that define us as explorers of the cosmos.